Welcome back to Calculus 2, Section 6.1, Power Series and Functions. We have three different topics to go over. We're going to define a power series, talk about the convergence of a power series, and look at functions being represented by power series. Let's get started. We'll recall a polynomial function. Polynomial functions are very useful in the study of calculus. What form do they take? They take the form of a constant plus another constant times x to the first plus another constant times x to the power 2, so forth and so on until we come up with our last term, a constant times x raised to the power n. The n is the degree of the function, and the constants c0 through cn are the coefficients of the polynomial. So a function of this form is a polynomial. Here we're looking at polynomial p as a function of input x. If we were to change out the input x for a translation of the x, namely x minus a, then the right-hand side is equally adjusted by swapping out x for x minus a. And again, this is the notion of translating horizontally the graph of y equal p of x. Well, a polynomial has a highest power on x, which we term the degree. The definition for a power series is to simply take all powers on x and add them together. So on the left-hand side, we have series notation. Note that we're now beginning the index at n equals 0 rather than 1. That's to account for the constant c0. We're interpreting x to the 0 as 1. And then we stop our index at infinity. In other words, we're taking all integer powers. So we have x to the first, x to the second, and so forth. All powers. This expression is termed a power series. And we have this notion of centering the power series, that we're taking the center of this power series to be 0. We can choose any center that we like. We can swap out the 0 for any constant a to update a power series so that it is centered at a. We simply swap out the x for the binomial x minus a. So in power series notation, here's how it would look on the left, and here's how it would look as a sum of terms explicitly written out. Very good. So we have power series, and we have this notion of a center of a power series. It's going to be convenient to work with a center at 0, but we're allowed to take the center at any point that we like. Note well that on the n equal 0 case, we are interpreting x to the 0, where x is any value, even x equals 0. X to the 0, we're interpreting to be 0. Likewise, x minus a, quantity to the 0, even when x is equal to a, we interpret that to be 1. Okay, so this is the definition of a power series. It's like a polynomial, except it's polynomials of all powers. We're seeing that we're writing down a series, which we studied in the previous chapter. Here we're now in chapter 6. That a power series takes inputs x, and we want to produce outputs as a finite value. In other words, we're interested in what inputs can we pass into a power series and produce a finite value. For what inputs x does a power series converge? All right, let's write down a theorem. For a power series centered at a, exactly one of these three cases will hold. That the power series will only converge at the center and diverge everywhere else. That's case A. Case B is that the power series will converge for any real input x. And case C states that only for inputs x, which are within a distance r of the center, will the power series converge. Any input which exceeds the distance r from the center A leads to the power series diverging, and that at the two inputs, which are exactly capital R away from the center A, the power series may or may not converge. All right, so looking at any power series having any center, that one of these three must be true. That's what this theorem is saying. What we now want to do is we want to establish this theorem. We want to prove it. And we're going to rely upon a fact. But first, let's look over what it means to have these three situations by looking at a number line. For case A, we look at the number line and we only highlight the single value for which convergence occurs, namely the center A. In case B, we have that we highlight the entire number line as all inputs x are valid. For case C, the more interesting one, we can only move away from A an amount r either up or an amount r below. We only highlight those values strictly within r away from A. Values which are strictly greater than r are not highlighted. And then it remains to be seen that two values exactly are away from A. So this left endpoint and that right endpoint, it remains to be seen whether we include or do not include as points of convergence. Okay, so looking to prove this theorem, we're going to rely upon a fact. Let's make the statement of the fact. The statement of the fact requires that we take a non-zero d. We'll assume that we have a sequence of terms, Cn, beginning at n equals 0. And we'll apply those terms one by one to higher and higher powers on d. We want to make the assumption that this series is a convergent series. And the fact is saying that if we take any value y such that the absolute value of that y is strictly less than the absolute value of d, then the resulting series also converges. Okay. Let's go ahead and prove this fact. Where are we beginning? We have a convergent series. What does it mean for the series to converge? Well, one thing is that the terms that we're summing up must go to 0. So we can make that statement that the C sub n product d to the n will go to 0 as the index n goes out to infinity. Well, if these quantities are tending towards 0, they're becoming small. Thus, we can look far enough along in the index n, find a beginning index capital N, and suppose that for all indices past this beginning index, that this quantity is small. And for convenience, we're going to use small as strictly less than 1 in absolute value. All right, well, what else can we do? Well, if we are beginning with information on a series given by terms Cn d to the n, but we want to make a conclusion on a series given by terms c and y to the n. Let's make a statement relating the sequence of terms c and y to the n to the sequence of terms c and d to the n. All right, so start with c sub n y to the n. Then rephrase that in terms of c and d to the n. Well, how can we obtain an equality? Well, it's easy. We just multiply by 1, the absolute of d to the n over the absolute of d to the n. Using algebra, rearrange in this fashion, and then take advantage of the fact that we know c and d to the n in absolute is strictly less than 1. That then allows us to throw away c and d to the n. In favor of 1, introduce an inequality. And now we have that y over d to the n, y over d in absolute raised to the n is always strictly bigger than cn y to the n. All right, so far so good. Now let's go ahead and take our condition of the absolute of y strictly less than d. So if we focus here on this quotient, y over d, we know that that y over d is going to be less than 1 in absolute. But then using this sequence of terms to form up a series leaves us with a geometric series which will converge since the common ratio is y over d in absolute, which is strictly less than 1. Therefore, we can look at the comparison test and see that the series defined by the absolute of c and y to the n will converge as term-wise each term of the sequence is less than a sequence defining a convergent series. But because we're using the absolute value of c and y to the n, we get that the series given by c and y to the n not only converges, but is absolutely convergent. Nice. That finishes the fact. Okay, so let's go back to the main theorem that we want to prove, which stated that any power series centered at A will have convergence at one of these three cases. Let's first restate the theorem so that we're not centered at A, but at a convenience, let's center it at 0. So how can we do that? We simply swap out the x minus a for a new variable y. Thus, when y is equal to 0, that's going to require that x is equal to a. Okay, so this is a trivial manipulation, and proving the theorem in this form is equivalent to proving the theorem in the original form. Good. So here's the theorem as we will prove it. And let's get started. All right, so to have this power series requires that we have a sequence of CNs. So let's have a sequence of CNs. And then let's make a definition. Well, this is a power series in the variable y. Let S denote all y's such that that power series converges. Okay. And then think of different possibilities. There's the possibility that S is just the value 0, y equals 0. But note that under that situation, that means that the only place where this series converges is at the center. S, by definition, is all values such that the series converges. If we only take y equaling 0 to be a value for which it converges, then by the definition of S, all other values lead to a divergent series. On the other hand, if we take S to be the entire real line, then that's going to give us case B holding, that we get convergence at all real numbers. So to neither be the first case nor the second case, let's let that be the third case. So now to finish our proof, we need to show that this statement of S not being only the center, as well as S not being the entire real line, is equivalent to this statement C. All right, so that's our task. Let's see how we'll do that. Let's start first with the second condition, that S is not the entire real line. Remember that S is all values such that we obtain convergence. If S is not the entire real line, then we can find a value, which is not just the origin or the center. We can find a non-zero value, which is not in S, since S is not the entire real line. Well, if y, and this is y tilde, if y tilde is not in S, and S means that the series you defined converges, then the y tilde is going to define a series which doesn't converge, or in other words, diverges. Easy enough. And now we appeal to the fact that we just established. Well, the fact then provides that if you look for any value greater than or equal to that y tilde in absolutes, that value will also determine a series which diverges. So, looking at S, find any value not in S, and then anything greater than or equal to that value in absolute will lead to a divergent series. Thus, S is contained in a bounded interval. The S is a bounded set. Well, there's a property known as the least upper bound property, which is a much more advanced calculus topic that we do not prove in an introductory class. But we may appeal to it and use that it gives a smallest upper bound. And we'll term that smallest upper bound R. All right. Next, let's use the second part of our statement, that S is not just the center. Because S is not just the center, then there will be some points other than 0, so either a positive or negative quantity. Whichever way that goes, positive or negative, that's establishing that our smallest upper bound, capital R, must be a positive quantity. And once we have that, as R is a smallest upper bound, then everything less than that value, capital R, in absolute must be contained in S. That's simply the definition of the smallest upper bound, which is exactly the statement of case C. And as we have all three cases, A, B, and C, verified, we are done with the proof of this theorem. And we may make some definitions for the notions captured by that theorem. Two different notions. The notion of an interval of convergence. We termed it S. We'll now call it capital I for interval. Are all of the inputs in the power series such that the series converges. So interval of convergence. And the capital R that we found in the proof, we're going to term that the radius of convergence. So for that case C, R was some positive finite value, and that we get a bounded interval of convergence, that we can only stray from the center an amount R, that if we stray less than R away, we have convergence. But if we stray more than R away from the center, we'll have divergence. On the other hand, when the radius of convergence is 0, then we cannot stray away from the center. we get that the interval of convergence is only the center. But if the interval of convergence is infinity, that means that, if the radius of convergence is infinity, that means that the interval of convergence will be the entire real line. Very good. So two definitions here. Interval of convergence, capital I, radius of convergence, capital R. And in practice, we go about finding capital R and then check endpoints to determine the interval of convergence, capital I. So let's look at an example. Determine the radius and interval of convergence. We have power series x to the n with coefficients 1 over n factorial. If we want to determine convergence of a power series, our default test is the ratio test. Recall that the ratio test gives not just convergence, but absolute convergence. Recall again, that's because we use the absolute value of the ratio of the next term over the current term. Looking at a sub n plus 1, x may be positive or negative, so when we write down an x, we always want to make sure to maintain the absolute values. N is a non-negative value, so we can throw away the absolutes when writing down n's. N factorial for the n plus first term is going to become n plus 1 quantity factorial. Here, this factor is a sub n plus 1 under absolutes. The absolute of a sub n appearing in the denominator means that we can multiply by the reciprocal of a sub n. We can make cancellations. N factorial will cancel with n factorial, leaving an n plus 1 in the denominator. N plus 1 copies in the numerator of x over n copies of x in the bottom leave us with 1 copy of x in the numerator. Don't forget that that appears in absolutes. Since x is just some value, some finite value, however small or large or 0, doesn't matter. Eventually, the index n is going to outstrip that numerator. Thus, whatever x you pick, the limit of this quotient is 0. Recall that we're doing the ratio test, so we can term that limit rho. And coming up with rho equaling 0 means that rho is strictly less than 1. And thus we have convergence, and convergence for all x's. If we're obtaining convergence for all x's, that means that the interval of convergence is the entire real line. And points on the entire real line stray away from the center. Note, what is the center here? The center is 0. That points may stray an infinite amount away from the center. Nice. Do another one. All right, same setup. Determine the interval of convergence and radius of convergence. The difference is that the n factorial was in the bottom in the previous example. Here it's in the numerator. In the previous example, the n factorial appearing in the bottom proved sufficiently strong to go up against any polynomial. All right, but now the n factorial is appearing in the numerator. And you have a competition going on between the factorial in the numerator and a polynomial. All right, so what do? We want to know the convergence, so we look at the ratio test. We have a sub n plus 1, swap out n for n plus 1, swap out n for n plus 1, maintain the absolutes on the x's, and write down the absolute of an in the bottom. Like before, we'll get nice cancellations. Simplified version is n plus 1 binomial product absolute of x. But no matter how small x is, n plus 1 will dominate, and this is going to tend to infinity. Finding that rho is infinity by the ratio test means that the series will diverge for all x's, But we know that if we plug in x equals 0, this will lead to a finite quantity. Thus, we get that r is 0, capital R 0. The only point that we can plug in is the center. And to highlight that that's the only point, we say that the radius of convergence is 0. And as was noted, this is showing that the factorial is much stronger than polynomial power. All right, let's do 3 different examples. One example for each of the 3 different cases given by the theorem. Here we have a power series where we have x to the n placed over n factorial. That would be an exponential versus a factorial, the exponential in the numerator and the factorial in the denominator. We're setting up an arms race between exponentials and factorials, and let's see which one wins. Remember that x is a variable, so x could be 0, could be a positive value, could be a negative value. If we're looking for convergence, then we're going to apply the ratio test. The ratio test is looking at the absolute value of the ratio of the next term over the current term. In writing down the next term, we want to place absolute values on the entire next term. Since n is a non-negative quantity, when we write down n factorial as n plus 1 quantity factorial, we do not need the absolute values. But since x is a variable, it could be negative 0 or positive, we do want to maintain the absolute values. Dividing the absolute value of the next term by the absolute value of the current term is the same thing as multiplying by the absolute value of the current term. And again, we require the absolute values whenever we write down an x. Very good. Make cancellations. N factorial will completely go away. Absolute of x to the n will go away. We'll be left in the numerator with the absolute of x. Down in the bottom, n plus 1. We're allowing for x to be anything at all, but that it is some fixed quantity. Just whatever that quantity is could be anything, but it is a fixed quantity. Whereas the n, we know that we want to take the limit as n gets larger and larger and larger. So at some point, n will outstrip the absolute value of x, meaning that this limit is 0. We know that 0 is strictly less than 1. Thus, in applying the ratio test, we're coming up with rho equaling 0. And rho strictly less than 1 means that we have absolute convergence. And as we did not have to specify a particular value of x, we get that we have absolute convergence for any x. Thinking of the 3 different cases given by the theorem, this is the second case, or that all real numbers lead to a convergent series. Using our new definition, that means that the interval of convergence is the entire real line. Noting that this power series is centered at 0, that's x minus 0 quantity to the n. And since the interval of convergence is the entire real line, we get the radius of convergence is infinity. Okay, and again, note that my comments on an arms race between an exponential and a factorial is showing that the factorial is stronger than the exponential. Very good. Let's do another example. And what we're going to do is we're going to bring the factorial from the denominator into the numerator. And now we can still have an arms race of this quantity n factorial up against this exponential x to the n. And we can think of, well, if we took small and smaller bases x is that going to be strong enough to overcome this factorial term, which wants to grow and grow and grow? So we're again looking at an arms race between an exponential and a factorial. We've already seen that the factorial is stronger than the exponential, and that should continue here. To see that that is the case, we set up the ratio test. Our nth term appears only in the numerator, so it's easy to write down. n+1 quantity factorial. N's are non-negative. We do not need to carry over the absolutes, but x could be negative, so we need to maintain the absolutes on the x terms. All right, good. And then divide that by the absolute value of the nth term. Make cancellations. We're left with n+1 binomial product with the absolute of x. No matter how small x is, it's not going to be enough to compete with arbitrarily large n's. This then will lead to a row of infinity. Row being infinity in the ratio tests means that we have divergence for all x's. And in particular, we want to think about that as x's not equal the center. What is the center? The center is 0. Pause for a second. Think if we were to swap out x for 0, that this would evaluate to a finite value. Pause for a second. What is that finite value? Quick quiz. Hopefully you said 1, since we have the n equals 0 term. All right, so since we have divergence everywhere for non-zero x's, we're getting that the interval of convergence is simply the center 0, and that we can produce no other value, thus we can only stray 0 away from that center. So the radius of convergence is 0. Okay, so that's 2 of the 3 cases given by the theorem. We'll now do a third example to go over an example for the third case. Okay, so same setup. We want to find the radius and interval of convergence. We want to apply the ratio test. Again, recall that x's are variables, but n's are non-negative values. So when we write down the ratio test, we only need to maintain absolutes when we involve an x. So here is the absolute of the n plus first term multiplied by the reciprocal of the absolute of the nth term. As we're plugging in for n plus 1 in writing down the next term, note that n swapped out for n plus 1, add in 2 leads to n plus 3. An exponential is never negative valued. Thus, we don't need absolutes on the exponential 4 to the n plus 1 or 4 to the n. Those guys lead to a nice cancellation. N plus 2 over n plus 3, if we form that up as a quotient, that'll limit to 1 as n is taken out to infinity. 4 to the n cancels with 4 to the n. X minus 3 binomial under absolutes raised to the n goes away completely, leaving us with 1 copy of x minus 3 in absolutes to the power 1. As we take a limit in n, we're going to get the expression, the absolute of x minus 3 over 4 as our value of rho. So in the previous 2 examples, rho had 0 dependence on x, and it led to a straightforward evaluation. Here, rho does depend on x. Let's go back and recall that to obtain convergence by the ratio test, the rho needs to be strictly less than 1. So if we bring that into our computation, that the rho, here depending on x, needs to be strictly less than 1, if we look at that, we can get rid of the denominator 4, come up with the numerator x minus 3 must be strictly less than 4. All right, so let's analyze this. Note that our center of this power series is 3, and that the x's can stray away from 3 no more than 4. Draw a nice little number line, pick off 3 on the number line, and then center an interval of radius 4, about 3. In other words, if we drop down 4, we'd be at -1. If we bump up 4, we'd be at 7. So we have first found the radius is 4. And then to determine the exact interval of convergence, we now need to test each of these endpoints. And that's straightforward. We just do it one by one. So the highlighted portion are x values, and we want to know whether to highlight the -1, which means we plug in for x, we plug in x equaling -1. Or if we're plugging in x equal -1, we look at the form of the power series. Becomes a series. Let's see. We would have -1 minus 3 produces -4. That's -4 to the n. You can apply properties of exponents to come up with 4 to the n in the numerator to cancel with the denominator, leaving you with a -1 to the n in the numerator, placed over binomial n plus 2. You'll recall by the alternating series test that this will converge. bn's as 1 over n squared are decreasing and tend towards 0. We get a check mark here, meaning that we will include -1 in our interval of convergence. On the other hand, when we plug in x equaling 7, 7 minus 3 is equal to 4. 4 to the n over 4 to the n goes away. 1 over n plus 2 is akin to the harmonic series, and the harmonic series diverges. Thus, we will include the left endpoint -1 and exclude the right endpoint 7. Thus, we've come up with the radius of convergence and the interval of convergence. All right, so the steps are ratio test. Ratio test, if it leads to a clean result not dependent on x, then you're done. If you have a result dependent on x, then you will come up with some finite radius r and have to do work to check the endpoints. Very good. So here are some examples for you to play with. And another one, if you've forgotten the binomial coefficient, here's the definition of the binomial coefficient. Later in this chapter, we'll work with the binomial coefficient more extensively. So it's a good idea to become well-versed, to refresh on the binomial coefficient. It's just defined in terms of factorials. Also go back and try and recall the importance of the binomial coefficient, how it can be interpreted as n choose k combinations. Alrighty, so that's the convergence of a power series, in particular the interval of convergence and the radius of convergence. And our friend is the ratio test. Good. Well, the ratio test was based off of the geometric series. Let's go back and recall the geometric series and see how useful it is in the setting of power series. Okay, on the left, we have a geometric series, an arbitrary geometric series. And then above the equal sign, we're giving a justification. When the absolute value of the common ratio is strictly less than 1, we can actually evaluate the geometric series as the very first term divided by 1 minus the common ratio. Let's clean that up a little bit. Let's suppose that the very first term is just 1, a is equal to 1. And that if we have the common ratio to the n, And note that we've changed also the starting point. Let's go back and look. Index begins at 1. The common ratio is n has exponent n minus 1. If we change that index from 1 to 0, then the exponent on r changes to n. Okay, so in this case, we evaluate, and the reason why we want to change the index is because then that mimics more closely the form of a power series. All right. So do something very trivial. Define this translation of the reciprocal function, f of x, as 1 over 1 minus x. Place a restriction on this f between -1 and +1 strictly. And then the role of x matches exactly the role of the common ratio little r in a geometric series of this particular form. So from that observation, we're then able to say that this function f of x, is going to be equivalent to a particular power series, for which we simply have to look at the geometric series. So by swapping out x for r, we can identify this function in power series form, and that it will hold for all x's strictly between -1 and 1. Rather simple, rather easy. Consider another function f. Instead of 1 over 1 minus x, if we consider 1 over 1 plus x, same restriction. Instead of letting x equal r, we can take advantage of the fact that 1 plus x is the same thing as 1 minus negative x, to then swap out negative x for r. So very nice. All we've done is found a form to match up identically with this formula, which suggests a substitution for the r and leads directly to a power series. All right, so here are some examples for you. Two different functions f, which we can match to the given formula. So in the first one, it should be simply swapping out r for x squared. In the second one, there are a couple of different points to pay attention to. First is the 4. The 4 needs to be manipulated into a 1. That means factoring off of 4 from the denominator, all terms in the denominator, as well as remember that the more general form for the value of a geometric series has a numerator of a. You'll want to let x squared take the form of a, the first term. All right, but besides those alterations, this is simply a matter of matching the form and then plugging in appropriate new values. And that brings us to the end of this video. Thank you so much for watching. Please like if you find the video useful, and I'll see you on the next one.